Okay guys, welcome to a new video. In this occasion, we are gonna calculate the electric field of an uniformly charged sphere. So the problem says a positive electric charge Q is distributed uniformly throughout the volume of an insulating sphere with radius r. Find the magnitude of the electric field at the point r at the point P, at a distance r from the center of the sphere. Okay, so let's answer. Let's go to the solution of this problem. The solution would be something like this. The system is a sphere, so because the system is spherically symmetric, the direction of the electric field is radial at every point of the Gaussian sphere or of the Gaussian surface. What I mean is this. If this is a sphere and this sphere has radius r, we are gonna draw a Gaussian surface. It could be inside, for example, it could be inside with radius r, or let me do this again. It could be inside or it could be outside. Actually, what we are gonna do is to calculate the electric field inside of the sphere and outside of the sphere. Okay, so this is a Gaussian sphere. We draw a Gaussian surface, a Gaussian surface. Why we draw a Gaussian surface? Okay, it's because we want to calculate the electric field at points on the Gaussian surface. All right. So what happened is that because the symmetric, this situation is spherical symmetric, the electric field at every point is going to be radial. So the electric field at this point is going to be radial here, right here, radial. At every point is going to be radial. Okay? Inside. And the same situation is going to happen outside. At every point here, the electric field is going to be radial. Okay? So, that's what happens. We can see that the electric field at every point is equal to the perpendicular component of the electric field. Why? Because at every point the electric field makes an angle of 90 degrees with the surface. The same happens here, 90 degrees here with the surface, and at every point it's gonna happen the same. Okay, so and because the total electric flux through the Gaussian surface is defined by this expression, electric flux is equal to the product of the electric field and the total area of the surface. In this case, we are trying to calculate the first, we are trying to calculate the electric field inside when R is smaller than the radius of the sphere. Okay, so to find the electric field inside the sphere, we choose this radio smaller than the radius of the sphere. We have to remember that the volume charge density is the charge divided by the volume of the sphere. Okay, so we are going to use this definition. The density is equal to the charge dividing the volume. Okay, that's the charge density. Okay, so for the whole sphere, this charge density is going to be equal to Q R dividing the volume of the sphere. But what is the volume of the sphere? Is 4/3 P radio cube. Okay, this is the density for the charge density for the whole sphere. Now we want to calculate the charge density between this Gaussian surface when R is smaller than R. We want to calculate the charge density. The charge density. And we use the same definition. The same definition is, in this case, this rho R is equal to the charge inside the Gaussian sphere or inside the Gaussian surface, QR, dividing the area, and in this case the area of the Gaussian surface is 4/3, the volume, P R cube. Okay, that's the charge density for the Gaussian sphere between inside the sphere when the radius is smaller than the radius of the sphere. So what I'm gonna do is I'm gonna call this equation number 1 and this equation number 2. Okay, what is this Q? This Q that I am pointing is the charge enclosed in the Gaussian surface. So I go to this illustration and I'm gonna trace lines. So the sphere that is the sphere where I am drawing these lines is the inner sphere. That's the sphere inside the big one. So that's the sphere that is enclosed by the Gaussian surface, and the charge in that sphere is this QR when R is smaller than the radius of the sphere. Okay, so there is another thing that we have to know here. Because the sphere is charged uniformly, that means that the density is the same at every point inside the sphere. At every point the density is going to be the same. That means that the density in the equation 1 is going to be equal to the density for the equation 2, because the sphere is charged uniformly. That means that the density is the same. So in order, with that said, we can equate the equation number 1 and equation number 2. We can equate those two equations, and the result is QR uppercase dividing 4/3 P R cubed equal to QR lowercase dividing 4/3 of P R cubed. These two terms, 4/3 of P, cancels with this, and the result is this: QR uppercase dividing R cubed is equal to QR lowercase dividing R cubed. And we cleared QR, this one, and the result is going to be QR is equal to QR multiplying R lowercase cube dividing R uppercase cube. Okay, and that's the charge enclosed in the Gaussian sphere. Okay, guys, I'm gonna call this equation number 3, and I'm gonna call this the charge enclosed in the Gaussian sphere. Okay, the Gaussian sphere is this case, the blue one inside, and outside is this. Okay, so if you remember that by definition the Gauss law is saying that the electric flux is equal to the electric field multiplying the area of the Gaussian sphere, and that's equal to 1 dividing epsilon 0 multiplying the charge inside the Gaussian sphere. If we replace the charge, the number 3, in this equation number 4, and we remember that the area here is the area for the Gaussian sphere is 4p r squared, and we know that this charge is the number 3 equation. We are gonna get that the electric field, the electric flux is equal to the electric field multiplying the area, but the area is 4p r squared, and that's equal to 1 dividing epsilon 0 multiplying the charge enclosed in the Gaussian sphere, that is QR multiplying R cubed dividing R uppercase cube. So this R squared eliminates with this term, and the result is E. Then we have E equal to E multiplying 4p equal to Q R dividing epsilon 0 R3. Okay, we clear the electric field, and we have that electric field is equal to QR R dividing 4p epsilon 0 4p epsilon 0 R cubed. Okay, and this is the result. We call it question 6. And this is the electric field when r is smaller than the radius of the sphere. So let's calculate the electric field when r. Let's calculate E when r is greater than the radius of the sphere. That means that we are going to calculate the electric field outside the sphere. Okay, outside, I mean at this point, outside of the sphere. Okay, so you know that the Gauss law says that the electric flux is equal to the electric field multiplying the area, in this case the area of the Gaussian sphere, and that's equal to 1 dividing epsilon 0 q r. But this is the charge of the whole sphere. We are not calculating a new charge because we are at points outside of the sphere. And what is the charge enclosed by this Gaussian surface? Okay, the charge enclosed by the Gaussian surface outside is the total charge, so we don't have to calculate a new one. And the charge is going to be the original charge. So this is going to be E multiplying the area of the Gaussian surface, that is 4πr squared. That is equal to 1 dividing epsilon 0 q r. And we clear the electric field, and the result is E is equal to q r dividing 4p epsilon 0 r squared. And this is the electric field when r is greater than the radius of the sphere. Okay guys, hopefully this exercise helps you to understand some physics about electricity and about electric fields. See you in the next video. Bye.